Welcome, friends. As I am a technician and engineer that's heavy on the fundamentals, we're going to explore something that is not a trivial problem to a lot of designers, makers, techs, and hams, and that is switches. And if you look back at my equipment back here, lots of switches. And so what do we make of this, Richard? Switches have been working for what, 100 years at least? More? Yes. I'm going to cover just what's called contact bounce. Here, let me give you that much. Well, actually, like that. Here, a little show and tell to demonstrate just what I'm talking about. Here we have, this is a cheap knockoff of the Microswitch brand. And here we have two contacts. These are the two contacts right here. Unfortunately, this is hinged at this point right here. And it's going to swing in an arc. Now you may notice that there's some doming here on this, and it looks like some dishing over here. That may just be something that I'm visualizing, or not visualizing, but imagining. But I'm pretty sure that this is domed. Either way, the action of this switch, that closes, and if you look at the arm, you can see that, yes, it is swinging an arc. Now, if these two faces are parallel, that arc is going to enforce a lack of parallel contact, unless it's at the end of the arc. It seems unlikely because I can see daylight at both sides of the contact interface. And well, that's good for a cheap contact. Let's look at an expensive one. Here's from the genuine Microsoft product. And here we're going to see there's a contact face here or just a rest. I don't know if this is a double throw. But certainly it's a single throw. And here we have two faces. And again, squinting hard reveals that, well, it looks like they're both planar instead of sculpted into a dish and accepting dish and a lost the term, a dome, yes. So let's look at the action of this switch. If you'll notice, this entire structure is moving as a unit in one direction. There's a lot of attachment points here, certainly, spring tension there. But in the action itself, those two faces are meeting, well, they're off center slightly, but the faces are meeting full on. And that's a considerable improvement over the first one. This is a illustration of what's called a reed switch. So I have what would be an upper jaw here, a lower jaw here, this wire going out to the contact, and this wire going out to a contact. I've enlarged them both here such that you can see that the two faces, I attempt to draw them parallel, and that's what you try to realize in real life. Now, these arms right here, well, we've lowered, this is absolutely fantastic over-representation of the mass involved at this level, but it's to accentuate the difference between this area closing and this area closing, and the tension along this beam and this beam to follow these masses and to close these switches or these contact faces quickly for one, squarely for another, and with enough pressure to maintain low ohmic contact. Those are very important considerations in switch design. However, these tips suspended out here, we have what's called a pendulum problem, because when this moves, it's going to impart a motion that travels down this at the speed of sound and reach this end later than this closes. And then this will move in response to that traveling wave, that physical wave. This too has a wave traveling down it that will eventually draw these two together, this whipping up and this whipping down. But this whipping action is going to pop those contacts apart, even though the upper jaw and the lower jaw are tightly gripped. And this is not this is not something you want in your designs, because it leads to this. This is a oscilloscope representation of two contacts bouncing against each other's faces. And sometimes we find that there's a complete opens, many frequent complete opens at its lower level, and many frequent closes up at this level, and something that's in between. These in-between states are very short bounces, such that the voltage droops through the capacitance that's held between the two opposing contacts, but it's a trivial amount of energy. But still in all, there's easily, well, a dozen. Now, if this line were tied to an IRQ, this is for you makers, if this was an interrupt request port, you would have, I would say, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, okay, 24 interrupt requests for one physical operation. This is not something you want to attend to. That's a resource hog. So what you do is, as soon as you hit it this time, you start a watchdog timer, and when the watchdog barks, you check it over here. You make sure that you put in a long enough time delay so that all of this bouncing will have settled down to a quiescent state, yes. So, returning to the ham shack here, that is the importance of contact health. And contact health is can be achieved through cleaning, but this last contact bounce, and in the graphic that I drew, this is a particular form of switch that's called a reed switch. And you'll find it in some large rack relays that have long arms that are the relay operation has a little hinge that kicks up, and all of that action has there's long elements, and this is not a trivial problem. For the equipment behind me, often a parallel series resistor capacitor called a snubber would have absorbed all of those hash for the same, say, it's about 10 milliseconds. And that serves everybody behind here, where that sensitivity in that 10 milliseconds is apparent. A lot of this equipment, that's just not a problem, and you may rarely come across this, but there's a lot of other hash that we're going to sift through before we get to that. But knowing this will help in future topics of Well, like keying. Keying, you're going to generate that same hash. And how you handle that is a different matter. Typically, ham radio operators, it's buried in all the other noise. Let's see, okay, I could ramble on here, but I'm going to close it and say that there's going to be more discussion on contact health and how to keep your contacts clean. So, thanks all, and 73s.